It's a privilege and a pleasure to introduce to you. He is already introduced. Karlheinz Brandenburg. Karlheinz Brandenburg has been a driving force behind most of some innovative digital audio technology, notably MP3 and MPEG audio standards. He is acclaimed for seminal work in digital and audio coding and perceptual measurement techniques, wave file synthesis and psychoacoustics. Karlheinz Brandenburg is a full professor at the Institute of Media Technology at Technische Universität Ilmenau. At the same time, he is director of the Fraunhofer Institute for Digital Media in Ilmenau. Thank you. Please. Oh, sorry, he's talking about recent development on audio technology. You can see that. Okay.
Okay, thank you very much for the kind introduction. Since it's past 12, I have to say good afternoon. So my talk stands between you and lunch. But still, I want to mention a few of the current developments in audio technology. And in fact, if you come tomorrow morning to the tutorial, you will see again some of the slides, because I won't miss out on these. There will be much more detail. Of course, that's the difference between half an hour and 3 hours. So I'll talk a little bit about high fidelity, just to introduce what people really want in audio reproduction. I'll talk a little bit about basic research, because other than many people expect, even today we don't know enough about how our hearing, how our brain and ears work. And there's some example application areas. Okay, just to introduce Fraunhofer a bit more, we are one of the 66 so-called institutes of Fraunhofer in Germany, and we have departments dealing with acoustics, especially spatial audio, all these 3D audio systems. We have a group working on media management and delivery with a lot of work in audio analysis. We have a department called Human-Centered Media Technologies, working a lot of evaluation and such topics as well. And we have a large group now in Oldenburg called Hearing, Speech and Audio Technology, where it's much more about speech, including speech recognition. Okay, let's go and let's look back 100 years when the phonograph was introduced and other early recording media. There's the story that Edison, who developed the first phonograph, really was a fan of hi-fi, as we call it today, of high fidelity. So for him, really, the quality was the most important. Let's listen to one of these early phonographs. Let's see whether the audio works. Okay, to be fair, that's how it sounds if we play today one of these old recordings. The quality at that time was a bit better, but still, okay, high fidelity. In fact, for Edison, this was so important that he sent out people working for his company in the world to do demos. And they really did blind tests, the first we know of. They did blind tests with a live cellist and the recording of the same piece of cello sonata on a phonograph. And the story is that people couldn't distinguish between the live cellist and the phonograph. Which, okay, we really can't believe these days. So what happened? One thing which could have happened was that, okay, the curtain took away so much from the sound that people couldn't really hear the rest of the difference. Maybe part of it, but that's not all of it. Of course, everybody could have been deaf. No, certainly. A lot of young people interested in these. So what else? One important aspect is that people were probably they liked so much that they heard sound again, and they didn't know yet what artifacts are and what noise is and so on, that they really listened to the music and didn't hear to what else was there in terms of problems with quality. The older of you probably all remember that once upon a time we all enjoyed listening to music over AM radio, which again is not really the idea of high fidelity these days. And of course there was one more thing from what we hear, the cellist practiced for a long time to make his cello sound like the phonograph. Anyway, so from that time people were dreaming of high fidelity. What would happen if we would do the same thing today? In fact, for one cello, I would say audio reproduction is in a state where it probably would work. We have very good quality. But if we don't have one cello, but a string quartet or a symphony orchestra, no, even today we can't do that in the same room to have the same impression. So, to get sound in a room in a way that we have the perfect illusion, we still are struggling. And all what we did before is only one part on the way. Okay, to understand all that, let's look at how our ears and our brain work. Things you've heard before, and there will be more detail tomorrow morning, but not too much, of course, is how our ears work. Pinna, ear canal, ossicles, cochlea, everything going then through the neurons to the brain. And then they have lots of processing in the brain. In fact, one way to distinguish these is that the masking, that we can't hear fainter signals if there's a louder signal, is really, can be explained mechanically. This is the mechanics of the ear. So, if anybody tells you that even with the best AAC encoded audio, they clearly can hear a different, then ask them who built their ears, because the normal ears we humans have can't do this. And the signals going to the brain really are basically identical between good audio encoding and the original. But then for spatial hearing, of course, the signals from both ears come together somewhere in the brain, and there the situation is completely different. That's really part of what's happening in the brain. And there, for listening, we use other modalities. What we see influences what we hear. What we believe influences what we hear. So there's a simple model drawn by my colleague Jim Johnston, which shows that we have several stops until we really recognize music. We have an auditory object analysis in the end, and before that we have some loudness, we have off this masking, the integration in the ear, we have feature analysis, and so on. What's very important, there is feedback, in fact even feedback to the outer ear, to the eardrum. So we can influence the signal coming into the ear, in fact even willingly. Other effects are automatic, but even then there is a feedback path from the higher levels in the brain to the lower levels and to the way we listen to music. So all that means that we get a lot of influence from other factors, and we need better understanding. So that's a part on basic research which is currently going on. In fact, it has been restarted at some points. There's a lot of research trying to build better models for the whole process of hearing. So, what are some of the effects? One is room reflections have an influence on localization. So, whether you are in such a room or a small room, very well damped, dry as we say it, or with lots of reflections, concert hall influences the way we listen and our abilities to localize somebody speaking. If we have somebody speaking from some point, of course the direct wave is what gives us the impression of localization, of where the sound comes from. But all the reflections help with that. In fact, we know that blind people use this effect. They can even derive room geometry just from listening. They walk, they put their head back and forth to have different directions, the sound coming from different directions to their ear using the head-related transfer functions. And with all that, they can sense a wall and stop before they crash into it. And some people make a virtue from that, even being able to draw the room geometry just from listening. Then, what we hear changes depending on the room where we hear. And there are some effects which show that drastically with headphones. That even with closed headphones, if you do the same experiment with virtual audio, you can get different impression, different so-called externalization, depending on which room you sit. Or there is, from 40 years ago, 1976 was the publication in Nature, the knowledge about the so-called McGurk effect. So somebody's just speaking some syllables, and again, it doesn't fit the picture, and your brain builds some other syllables. So it's really, you hear something different. We all know that our eyes sometimes deceive us, but this is happening even more with our ears. So learning, adaptation, all that changes the way we listen. Some simple corollary. If you get some nice high-fidelity equipment, you see a lot of them here at IFA. If it's well designed, it will sound better for you. Don't do blind tests, but otherwise it will sound better. Okay, so people are really trying to build ultimate models of listening today. So again, we have all the old models, including the so-called cocktail party effect, which allows us to pick out one person from a group and so on. But there are questions which are simple to ask and will take a lot of PhD work to get somewhere, like can we quantify the influence of rooms on perception? Something we did in Ilmenau, exact reproduction of a signal at the eardrum is not enough to give you the same impression of audio. You can still have large differences. Then something I learned the neurologists call neuroplasticity of our brain. I used to call that just learning. Is really that we know that training for everything which is in the brain, not the mechanics of the ear, but everything which is done happens in the brain, that is listening, is changing over time. And the simplest and biggest question is, what are the necessary cues? What do we need to do to generate perfect auditory illusion? Okay, let me give you some examples of that work. and some examples where people work today. Some of this is already in the process of application. Some of that people have tried to say it's been solved for a long time, but in reality it's not solved. There's still lots to do. And 3 of these examples will be about sound in rooms, and then I'll talk a bit about music information retrieval, how we automatically can analyze music and use that. And again, for all of this, there will be more tomorrow morning. So, immersive sound. Any Trekkies out here who love Star Trek? Who knows Star Trek? Who knows the holodeck? No? Times have changed. It's only a few people, yes. So you know the holodeck. And a lot of technical development, in fact, we can find early ideas in science fiction, and the holodeck is a nice symbol for something we would like to do, where people with all this virtual reality technologies try to get there. But the holodeck in the movie does it much nicer. You just walk into a room and you feel like you are somewhere else, and you can feel it, you can smell it, you can see it, full 3D. It's a holodeck. And in fact, for audio, we try to do the same, to get you into a room and have the perfect audio illusion. In fact, for movies, people already do a lot of computer-generated pictures. Computer games, by definition, never had that difference. So we have a lot of CGI technologies on the graphics. But again, the question is how to do the audio. In fact, if we go back in audio, this started, okay, some people here are old enough. I remember when quadraphony was the newest and best thing, quite some time ago. It never made it, but then surround technologies with matrixing came back via the movie industry and made it. That's simple with a lot of problems. There's been ambisonics around for a long time, and there's newer systems using vector-based amplitude panning, wave field synthesis, and so on. And just to do some advertisement for the program, tomorrow, early evenings, there will be the tour to the time lab, and there you can really get great demos of these technologies in video and audio. So they got a wave field synthesis system, they got a large display, and I don't know whether there will be any 3D demo there tomorrow. Maybe, okay, so with the glasses. Okay, but what to do with audio? Yes, once upon a time we had mono, as we said, this works good today. We had 2-channel stereo. We have to sit on the right line, and then it can sound great. People went to 5-channel stereo with some big problems, and that's the so-called sweet spot, because that really, from the experiments which got people to say, okay, 5 channels are enough. Yes, 5 channels are enough if you are at the right spot in the middle and don't turn your head. So it should be screwed somewhere that you don't change it, and then it's good enough, because you can't distinguish anymore. If you sit at a different place, or you can move your head like the blind people do all the time, then things change. And in fact, in the real living room, no, that's not, where's the sweet spot? Nowhere, not where people sit usually. So there's all kinds of ideas how to measure room acoustics and do delay compensation automatically and all that. And from what I hear, it's usually not used. People don't do it. Okay, then there was late Michael Gerson who said, okay, let's use mathematics. How can we describe the wave field? Let's do so-called spherical harmonics. And from that we know the higher the order, the better we can actually get the actual reproduction if we do it the same way. So initially it was just first order, so-called B format, good for some nice demos. Then people found out, oh, if we do higher order, we can enhance the sweet spot, because originally B format has the same sweet spot problem as a 5-channel setup. So there you can enlarge the sweet spot, and in the end you recreate a wave field which is like the physical wave field. So it's just a harmonic approximation to the real wave field. First order is amplitude, then you go into the different directions, and then you can have more and more complicated directions. Nice idea, and there's more and more people who think that will be the future, but it's not the only way to do it. The other school of thought, in fact, had different starting points. People in Finland starting with so-called vector-based amplitude panning, just saying, okay, let's get the sound from the different direction and let's do the same as we do in panning in 2-channel stereo, but with more advanced formulas, really taking the signal vectors in there. And if you combine that with right delays, it can work very nicely. In fact, it's the method of choice today in a lot of systems. The other idea came from some work in Delft at the Technical University there. And it's called wave field synthesis. And that's, in fact, an implementation of the wavefronts simplifying from the Kirchhoff-Helmholtz integral. So I think we have a lot of electrical engineers here who once upon a time heard about that integral, and it just tells you that for fields like the wave fields, if you have the right equations, then if you know on the surface everything, then you can derive the pressure, velocity, everything, density functions at every point inside and outside, which of course is not practical. But people did some simplifications to that, sampling, taking instead of the 2 parts only 1, then it's correct inside and incorrect outside, which people don't care about, and so on and so on. And that gives you systems with many loudspeakers. In fact, combining that with the ideas of vector-based amplitude panning, now we have algorithms which use only a lower number of loudspeakers. But anyway, if you have more, you can have more nice effects, and you can create a wave field in a listening area. And again, tomorrow, late afternoon, early evening, you will be able to listen to that. I promise you a great setup, great demos. Okay, so that about audio there. And in fact, we see in the moment that some simpler systems like Dolby Atmos try to push into the market. You can see them all everywhere here in the where you see audio AV receivers and audio amplifiers at IFA, and other systems are on the way. People are currently discussing standards. We'll still see some progress. There are some unsolved questions. And one of the unsolved questions is, all this works best in a dry room. If you have a cinema, it's fine. You have controlled acoustics. If you would put such a system into this hall, I can promise you, you get into trouble. If you get it into a smaller seminar room with walls like this here, it really wouldn't give you the full illusion, because our brain is too good at recognizing rooms. If you do it in an anechoic room and you have the right signals from the loudspeakers, the brain gets the same signal as really in another room. You get a very nice illusion. If you do it in a smaller room, your brain says, oh, just 2 minutes ago I heard somebody speaking and I heard all the reflections. I know the setup of the room. Even if most of us couldn't draw the room, they still have this ability to recognize the room. So, and now there is some signal which tries to sound like there's some sound coming from outside. But I hear this signal and I hear the reflection from this wall. No, no, no. Triangulate, the signal is coming from the loudspeaker, not from somewhere else. So the illusion breaks down. We hear loudspeakers again. So that's part of the problem. Can we do something to cancel these reflections? Can we cancel out unwanted sound? Now that's a different topic, but it's very much related. In fact, every year somebody tells me, oh, I have something for you to invent. I want just to have some 2 loudspeakers here, and can you keep the noise from the street out? And I have to say, no, there's some slight problems with physics. If we have just one place, like the ear canal where the signal goes, then we all know the noise-canceling headphones work very well. There it works. But to get this working in a room is much more difficult. With enough loudspeakers and enough microphones to really catch the sound field in the room, theoretically this could be possible. But, and that's a picture from a setup in Erlangen from the university there. If you have just 48 loudspeakers, just some 10 microphones, you have 480 echo cancellation paths to calculate your algorithms. And that's just not only a problem of the amount of calculation, it's a problem of numerical stability as well, if you do this. So that doesn't really work. And our friends in Erlangen have done some algorithms to, as done in other fields in technology as well, say, okay, if we can't do it in time domain, let's just use an appropriate transform. And they call it the wave domain, and there it's much easier to do the echo cancellation properties. Only problem even there, while it's easier than with the 480 paths, it's still only simulations. We haven't seen any real-time implementation of it. We hope it will be there, let's say, early next year, but still can't say. Next problem. We get this great sound over loudspeakers. And then there's a lot of occasions where we want to listen through headphones. And people have said, okay, if I listen to loudspeakers, even with a good 2-channel setup, I have the feeling of a sound stage. I have a feeling somebody standing there and here are the instruments. If I have my headphones on, everything plays within my head. What to do? So we have this in-head localization, we get front-back confusion, and in the end it doesn't feel real. So people have worked on that again for many decades. And again, this is one of the problems where people announce they have solved it, and it's not finally solved, even until today. And even at IFA here, you can go to TechWatch, to other places, and you see people, again, who say they have solved it, and if you do more discussion, you will find out, no, it's not a full solution. It's only, again, a partial solution. So this started with dummy head recordings a long time ago, which is good in the sense that, on one hand, It retains the time and phase relationship. Our other so-called normal stereo, at least in the old times, all was intensity only because it needed to be monocompatible. If you have 180-degree phase shift parts in a signal, they would cancel. So everything needed to be monocompatible. So with dummy head recordings, you have phase, you have the proper reproduction of time differences, and since it goes through a model of your head, you have some head-related transfer function. It's not yours, but it's one. So sometimes you got great illusion, only sometimes, unfortunately. Next thing is, we know that the head-related transfer functions, the transfer functions of sound coming to our eardrum and being modified by pinna, by torso, by head form, by ear canal, and so on. This is very individual. We hear differently. We learn to hear with our HRTFs all our lives. And it changes over time as well, by the way. So next idea was, okay, let's individualize it. Let's really measure HRTFs and then do the proper reproduction. Works better, but again, not enough. Next thing, okay, but we know head-related transfer function changes if I turn my head. If I turn my head and the sound doesn't change, of course this must be in head localization because that's the only place the sound can come from if it doesn't change if I turn my head. So the next thing is use head trackers. Much better. Still sometimes a problem. Works in a lot of cases, but not always. Next thing is, okay, use proper room simulation in addition. Again, another proper influence. And the system, I won't say which commercial system it is, but there is one out there from, I think, an Irish company, which uses training. It does all of the above. So you get a little microphone in your ears. You see loudspeakers and you have to adjust the volume. So you train a little bit and then you get the sound and then you get a sound which coincides with what you've heard before, with the 5 loudspeakers of a 5-channel setup you've heard just a moment before. And that can quite often give you very good illusion. But again, commercially, it's not that successful because people don't want to go through all these. So again, there's a lot to do. Then, one more topic, music information retrieval. We have lots of music, and the question is, how do we really cope with that? So usually I'm asking anybody here with more than 1 terabyte of music on their computers? Not here, not that many audio people. Well, no, quite some people who have that much. And if you translate that, okay. If you translate that, depending on what compression or not you do, that may be years of uninterrupted listening. So people just don't know what they have. Or if you use one of these new streaming services, you have literally the choice between 35 million tracks or such. So how do you find what you like? And that's something where people have done work to get your idea of what's my favorite music and translate that, to recognize music. You know, Shazam and similar services. So that's all called music information retrieval, and the basic system which is used most of the times is really the query by example. You use machine learning, you have a number of features, you have models, you get to distance measures, and then you say, okay, which is closest? And again, much more detail on that tomorrow morning. Just for people who want to see a little bit more of mathematics, there's different steps in there. One is the feature space reduction with, for example, generalist Markov models, support vector machines, and so on. And with that, you can recognize music. That's scientifically solved. So 12 years ago, we had 99 point something of accuracy over difficult connections and 100% solid for even large databases over simple connections of audio. So, sorry, not a good idea to restart research there. We can do it in a way that it's good enough. Other things are not so easy. There's the idea of recognizing melodies, just from humming or singing. And we had quite some work on this in Ilmenau. We put that into a prototype and did some tests in an electronics market in Munich a long time ago. We called it the top 100 search engine. And people were singing or humming, and we did anonymous recording. And that showed the problem of this, because for more than half of all these recordings, neither the machine nor any human stood any chance to recognize a melody. Okay, just finally to give you some pictures of current applications. If you ever go to the Bregenz Outdoor Opera Festival, there's a very expensive, very complicated audio reproduction system there using a combination of different technologies, 800 loudspeakers, and yes, it's great. Then planetaria use such technologies more and more, Jena, Hamburg, a few more. And yeah, if you can see here, there are a lot of loudspeakers in there. So people are thinking of bringing such technologies to cars as well. Okay, let me conclude. In a video-based, video-determined, or a world where video really looks as the most important things to a lot of people, audio often is an afterthought. But if you think about communications, you need good audio for communications. So audio is a big part of an overall media experience. Our ears and our brain are very fine instruments, capable of registering really very minute details. So that's very important. We can only marvel, but even then, some things we can't hear, and we have to know that. And if we can't hear something, we start to believe instead of knowing, instead of listening. So audio is subject to I hear what I expect. If somebody tells me it sounds better, if somebody looks like it will sound, it's more expensive and will sound better, then subjectively it will sound better. There's continuing progress, but it's not finalized regarding sound in rooms. Some old questions are still unanswered. So for people in research, it's good news. There's plenty of research still to be done, and I'm really happy to be involved in that. Okay, that concludes the talk. Thank you very much. Okay, Tom has a question.
I had a question. While you're doing this, I was just thinking, there's one side that you're not looking at. That is, you look at it from the outside. How about if we also have a compensation mechanism from the inside? What if you could, for instance, somehow modify the internal neural processing capabilities to get some of these, or to modify the effects to be able to do more canceling, effective canceling?
I think that's what we call learning. And that's what actually we look into as well, whether there are some simple training methods which help you with that. But of course, there's a problem of psychology again. So can you really convince people to go through a training procedure for some of this?
Yeah. You gave some examples of people asking you for noise cancellation in streets, for instance. I'm thinking on a more specific and more constrained problem, the one of speech recognition, which is a lot affected by surround noise. In this more constrained problem, let's say in a range of 3 meters, why are the current speech recognition systems still suffering so much from noise?
This is a very good question. And I just can say I have the same impression that speech recognition in noisy environments really doesn't do it yet. We sometimes get questions from car manufacturers, for example, like it would be great to do it better. And our group in Oldenburg now is looking into exactly that problem. But whether they will be successful to announce a breakthrough next year or 5 years from now, I won't promise.
Questions? If not, we thank you very much for
Okay.
this very nice question talk.